Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. So we were starting our series of organic lectures in which in the previous videos we have dealt about something called hyperconjugation, and in the previous lectures we had dealt with inductive effect. So to carry on further, the third topic or the third important effect observed in any organic compound is resonance. So resonance in general, it means cumulative effect or the additive effect of something. Now, what does this have any role in organic chemistry, right? So, let us understand what resonance is and how it adds up to the stability of the organic compound. Actually, resonance is a very important effect, even more important than inductive effect and hyperconjugation also. So, actually you can consider the series of lectures we were having on organic compounds, basically inductive effect, hyperconjugation and resonance. We are basically going in the ascending order of their importance, right? So, inductive effect, although it is a permanent effect, but is comparatively weaker effect. It is dominated by hyperconjugation. Again, hyperconjugation is dominated by resonance. So, let us see what resonance is. So, first of all, you all know the Lewis dot structure, right? In the lecture of chemical bonding, we have dealt with Lewis dot structure. In Lewis dot structure, what we knew is we are placing the atoms together, and the electrons present in the outermost shell of the atoms, they are represented as dots. Okay, the dots basically signifies the electrons. So, most of the covalent compounds have a unique Lewis formula, which is the dot structure, but these Lewis formula explain the bonding in that molecule, but there are many possibilities, like there are n number of ways or more than one ways where we can draw a particular molecule, right? So, but for many molecules, two or more dot structures are feasible rather than only one structure. The phenomenon of resonance was put forward by Heisenberg. Okay, Heisenberg is a very eminent personality considering atom, because Heisenberg's uncertainty principle was a challenge to Bohr's atomic model. Okay, so Heisenberg was the person who proposed the concept of resonance. Okay, he was the one who said there are more than one Lewis structures that can be possible for any organic compound. So the phenomenon of resonance was put forward by Heisenberg to explain the properties of such covalent compound where more than one structures are possible that could not be represented by a single structure. For example, the formate ion can be represented by two equivalent structure. Okay, now if you see, yeah, this is the formate ion. How it is formed in the first place? We have, sorry. So we have formic acid, HCOOH. What is the structure of formic acid? Now when this formic acid loses one H plus, okay, when this H plus is lost, this is the acidic hydrogen because it is connected to a more electronegative atom, oxygen. Okay, so when this H plus ion is lost, what happens? H plus is removed out and we are left with HC double bond O negative, which is this. Now this negative on this oxygen, suppose I am numbering it 1, this is suppose 2. So I can say there is a negative charge on the first oxygen, but it can also be possible that there will be a negative charge on the second oxygen. How? See, if this negative charge is moving here, then this will move here. There will be a movement of bond. Why? To restore the tetravalency of carbon. Carbon cannot form more than 4 bonds. Okay, so in order to restore the tetravalency of carbon, what will happen if this negative charge is moving on to this bond? This double bond will ultimately shift its pi bond to its oxygen atom, because pi bonds are again weaker bonds. They are easily broken down. So here this is one feasible structure. The other feasible structure is like this, where the oxygen number 1 is doubly bonded and there is a negative charge on the second oxygen. So such different structures are called resonance structures, and the actual molecule is a combination of both the structures, structure A as well as structure B. So I can represent it as HCOO, and there is this electron cloud around the OC p-o linkage. Okay, there is an electron cloud. This actual structure, which is basically an intermediate structure of both the structures, is called as resonance hybrid. Okay, it is a hybrid structure and that is the most stable structure. Okay, it is called resonance hybrid of all the structures. The resonance structures are simply alternate Lewis structures for a given ion or molecule. Okay, the resonance structures are basically the probable Lewis structures for a molecule. In what way we can represent the Lewis structure of a molecule are simply its resonance structures. Okay, resonance is playing around with the pi bonds, basically moving the pi bond from one atom to another. Now, we have to see the characteristic of resonance or the resonating structures. Again, this is a very important part. Resonance exists only in those parts of the molecule that are composed of sp or sp2, where there is basically a lone pair of electrons or negative charge. Okay, composed of sp and sp2 atoms, and p orbitals are an absolute requirement for resonance. Okay, p orbitals has to be there. And what p orbitals? The parallel p orbitals, those not involved in the sigma bonds. Hence, it does not occur in sp3 hybridized carbon. Okay, in sp3 hybridized carbon, all the valencies are satisfied by single bonds, and single bonds are stronger bonds. They are not likely to move. Okay, therefore, they are not allowed to move in the molecule. Therefore, where the structure is entirely, all the atoms are singly bonded in that structure, in those cases resonance is not observed. All the atoms in the molecules taking part in the resonance should be coplanar. They should be present in the same plane so that transfer of pi electrons from one atom to another is possible. Okay, they must be in one plane. Okay, this is necessary for effective overlapping of the pi orbit of the p orbitals. The p orbitals must be effectively overlapping. That means the situation or the condition must be apt for the movement of pi electrons. If the pi electron has to jump from one plane to another, it will not be feasible for it. Okay, so there resonance, the condition of resonance breaks. While making a resonance structures from other, electrons move between the adjacent atoms. Only the electrons can move between the adjacent atoms. It cannot shift from the first carbon to the third carbon. Okay, it has to shift from the first to the second. Only adjacent carbons are shifted. Adjacent atoms, so two adjacent atoms, it is shifted. Types of electrons that can be moved are lone pairs or pi electrons or a negative charge. Basically, the loosely held electrons are allowed for movement. Okay, what are those? Lone pairs, pi electrons or any negative charge. Or the unpaired electrons, obviously lone pair of electron, unpaired electron present on radicals, that is free radicals. These electrons reside on a resonance donor atom. Okay, the atom on which these conditions are present, that atom is called as a resonance donor. Okay, that is the donor atom. That is the site from where the electrons or the negative charge moves. Okay, and move to the resonance acceptor atom. Fair enough, the atom having a deficiency of electron or the atom which accepts that electron coming is called an acceptor atom, which must be adjacent to the donor atom. Okay, the acceptor atom must also have an open octet to be able to have another electron pair. Open octet again means deficiency. Okay, an atom with a formal positive charge can also be a resonance acceptor atom. In any way, what it signifies is, in any way, the acceptor atom must have the ability to accept electrons, must be deficient in electrons basically. An atom with a formal positive charge can also be a resonance acceptor atom, as long as the atom does not accept more electrons than it can normally accommodate. Okay, it can be it can take up electrons until and unless it has fully satisfied its octet. Basically, the atom should be deficient in electron. This is the gist or the moral of this point. So, if I see this one, what I can see is this carbon particularly, it has a negative charge. So, I can categorize it as a donor atom. Now this donor atom donates this electron to its adjacent atom. Okay, this is the adjacent atom, and here see this condition is apt because the adjacent atom is deficient in electron, right? Lone pair of the resonance donor, this is the open octet which is the resonance acceptor, and the curved arrow indicates shift of electron pairs. And basically if I am showing arrow like this, the head of the arrow must be pointing to that atom to which the electron is shifting. Okay, after the electron has shifted, it will be appearing in the form of a bond obviously. So this pair can be similar to this. Okay, the double bond will be formed between these two carbon atoms. Got it? Next is resonance hybrid has a lower energy and greater stability than all the contributing structures, or the contributing structures are otherwise called as the resonating structures, and the resonance hybrid has a it has some minimum energy and higher stability as compared to all the resonating structures. Also greater resonance energy, greater the stability of the atom. Resonance energy means amount of energy released for transfer from one resonating structure to another. So if an atom is releasing out all its energy, then it's going to a minimum energy state, and energy is inversely proportional to stability. So if the atom is going to a minimum energy state, then the stability will increase. Okay. So for the resonating structures, the position of nuclei must be the same. Okay, the nucleus of the atom, the center remains the same. The only movement allowed is of the free electrons, which is pi electrons, lone pair or negative charge. Okay, only those loosely held electron pairs can move. The atom as such does not shift. Okay, remember this one. If I am saying 2 carbon atom, that means only the pi electron if present, then that pi electron will shift. This carbon atom will not go on taking its negative charge to give to its another atom. Okay, the carbon atom remains intact, only the loosely held electrons shift. Got it? Okay. Then for the resonating structure, the position of the nuclei must be same in all the structures, and the total charge also must be constant. You cannot add or remove any charges for that matter. Those structures which have little contribution, where negative charge when separating arises to ion is on less electronegative. That means that structure in which the negative charge is on more electronegative atom, that is stable. If the negative charge is on the less electronegative atom, that is unstable. That structure is unstable. All resonance structure must have same number of unpaired electrons, and the structures with similar charges on adjacent atoms are insignificant due to electrostatic repulsion. That means if I am having a chain and I am having both the carbon atom as negative, then this structure is structurally wrong, because these negative charges, they will have electrostatic repulsion, they will repel among themselves. As a result, the structure will distort. Okay, due to electrostatic repulsion and consequent instability. The resonance structures with greater number of covalent bonds are more stable. If there are greater number of covalent bond as compared to charge separation, that structure is more stable. Thus, non-polar structure of formic acid is more stable than any other resonance structure. Okay. Now, if I see this one, here what happens, there is a negative charge on the oxygen atom and a positive charge on this oxygen atom. Okay, because the lone pair has shifted to this. Due to this lone pair shifting, what happens, the charge separation has arisen. Then what happens, if I see here, then there is less formal charge structure, and hence this is a better Lewis structure than this. Okay, how it is basically formed? This lone pair, oxygen was having 2 lone pair, 1 lone pair is given to the bond, and this bond was shifting on this, so it is having a negative charge and it's having a positive charge. There is charge separation, and again see, oxygen is a more electronegative atom and it is having a positive charge on itself. That's why it's also a very unstable structure. So basically, the structure where there is less charge separation, that structure is your stable structure. Okay, then we had almost dealt with the key concepts of resonance. In the next video, we will be dealing about some questions regarding this. But here, first let us understand 3 things. One is, okay, the first and very important condition for resonance is the presence of conjugation. But before going to what is conjugation, you have to understand 3 terms: conjugation, cross conjugation and non-conjugation. So basically conjugation means alternate single bond and double bond. Okay, that means there has to be alternate single bond and double bond. If I see, I have three structures in between and like in front of you, 1, 2, 3. If I look at this structure, what happens is I have one double bond, then single bond, then double bond, single bond, double bond, single bond, double bond, and so on. So here what I see, there is alternate single and double bond. That means this is a case of conjugation, right? This is a case of conjugation. So here resonance is possible. Now if I see cross conjugation, look at this structure. This is a benzene ring where all the carbon atoms are in conjugation with each other. Okay, if I compare this also, this is a benzene ring. Here also all the carbons are in conjugation with each other. There is alternate presence like double bond and single bond. But look at this carbon and this carbon. This carbon is intervened by a carbon which extends the conjugation outside the ring also. For example, if I am considering this carbon, for it there is a single bond, double bond, single bond. So this part there is conjugation. Now if I look at this carbon, double bond, again I am having a single bond and double bond. This basically extends the conjugation. See, double bond, single bond, double bond, single bond, this and again a double bond. So this part extends the conjugation outside the ring. Okay, so this is a case of cross conjugation. Where two carbon or two or more atoms which are in conjugation, they are intervened by a third carbon atom which extends the conjugation outside the ring or the chain. That's the case of cross conjugation. Now if I see non-conjugation, pretty simple. Third example, this is double bond, single bond, single bond. There has to be a double bond after a single bond, but it is not there. Here the conjugation is broken down. Now if I say here double bond, single bond, single bond, again conjugation is broken down. Double bond, single bond, single bond. Here again the conjugation is broken down. So basically this is not a conjugated system. Which is not a conjugated system at all. It is called non-conjugation. Okay. Now the question arises, in what cases resonance are possible? Only in case of conjugation and cross conjugation is resonance possible. In case of non-conjugation, the resonance is not at all possible. Okay. Resonance is only possible in case of conjugation and cross conjugation. So these are basically all the key concepts you were required for understanding what resonance is. In the next lecture, we will deal about some questions regarding resonance. That's all for this video. Thank you.